Hi, everybody. Welcome to an activity day focused on some of the past FRQs that we've worked on in this room, or in this class rather. What I've done is analyzed some of the questions that I have assigned you from a couple angles. One of them is questions that many people made the same simple mistakes on. And the other angle that I looked at were questions that have a high probability of being asked next week. So by marrying those together, I have handpicked a selection of FRQ questions that I would like to do with you from scratch. Now, the only disadvantage we have in this forum is that I don't have a way to constantly show you the FRQ itself while I'm answering it. What that means is I will flash it to you and then work on my page here. So while I still hope you copy what I write because you'll be, working on good chemistry, if you have access to your FRQs, if you've got a solid place that you've been storing them throughout the school year, it might be beneficial to have those handy, because you could directly compare what you have to what I'm doing. But again, even if you don't have those FRQs handy, I still believe this will be a rich experience for you as I model some of the best practices for these revisit topics. So overall, I'll have time to answer 4 full FRQ questions with you today. And I'm going to post a secondary video of me doing some more also for those of y'all that enjoy this activity. So anyways, I would like to start on Unit 2, which was reaction postulations, and take a look at one of the very first new skills I taught you. This reaction says when rubidium sulfate is heated and mixed with strontium perchlorate, the reaction produces a great deal of energy, including a burst of flames and the production of crimson smoke. And then it wants us to analyze this reaction from 3 different ways. It wants us to write some different ionic equations, it wants us to draw a particulate, and it wants us to run stoichiometry. So while we're working together and you're working along with me, please interrupt me at any moment you'd like to if you need clarification on something. All right, so first off, all right, part A has 3 parts, so we got to deal with that. But we want the chemical equation for rubidium sulfate and strontium perchlorate. Now, keep in mind, I have told you that these words sulfate and perchlorate do not dictate that you need to have a memorization of the polyatomics. Now what they'll do is if they mention sulfate like this, they will also identify that it's SO4 - 2. So it'll make it so you can easily build these compounds correctly, because of course in my rubidium sulfate, sulfate will cross a 2. And then in the strontium perchlorate, you definitely know that strontium will cross a 2 to the perchlorate that you would not have to memorize. So there's the given reactants, and it wants us to first write the reaction. All right, so this is double replacement. There's going to be an exchange of these cations on the other side. So I just need to swap their places, in which case we will create strontium sulfate and rubidium perchlorate. All right, you'll notice on the other side there are no numbers being crisscrossed because it's +2 - 2 and +1 - 1. Now, we're not balanced. An unbalanced equation is never good, but it turns out if I put a 2 right there, it will fix it. All right, now there's 2 rubidiums and perchlorates on each side, and everything else is happy. Now, if you want to be extra good, I can use my solubility rules to label the solubilities of these guys. If you have forgotten your solubility rules, you'll want to go and revisit Unit 2. It's in your notes there, all right? But my alkali salts are soluble. Perchlorate is always soluble. Sulfate is usually not soluble, and perchlorates are always soluble. So I just followed the rules that are in your brain. All right, so I did the first thing. All right, that's the chemical equation. Now let's get into the better skill. It starts with complete ionic equation. If you remember, that's where everything that is going to dissociate will be dissociated, whether it's a spectator or not. So let's separate everything. So we'll start right here. All right, we have aqueous rubidium sulfate. So I'm going to show that. All right, but the only thing here is, remember, when turning a balanced reaction into a complete ionic, the subscripts can become coefficients, right? Because I need 2 rubidium ions floating around upon dissociation. But there's only one sulfate dissociating, so I'll show him. All right. Aqueous, so show the dissociation of this salt also, and you'll have 1 strontium. And notice it's 2 perchlorates. My precipitate is obviously not dissociating, so keep the solid together. And then we've got dissociation here with 2 rubidiums and 2 perchlorates. In order to do the last part, my net ionic, that's where the spectator ions need to disappear. So anything that duplicates itself as a reactant and a product, I see 2 rubidium ions on each side, so we can get rid of those, and 2 perchlorates on each side. All right, so that'll leave us with our net ionic of everything else. Bring down the strontium. And hooray. All right. The next thing wants us to do a particulate diagram, all right, of the products, just depicting the products, and it says to make sure that you show any dissociation that took place there. All right, so my products are focused up here, and there was dissociation for the aqueous item, but not for the precipitate. Now, keep in mind that while we're drawing our particulate, the state of matter is important because we want to show the state of matter via our drawing, but the ratio is important too, all right? It's a 1-to-2 ratio here, so watch how my drawing mirrors that. All right, so there's a container by which we can get our particulate drawn. All right, my solid, of course, needs to be organized predictably along the bottom. So this can be my strontium sulfate. Now look what I did, and this one I just decided to do this. I drew 2 of them. I could have drawn 1, I could have drawn 3, as long as I was organized about it. But since the ratio is 1 to 2, and I drew 2 of these, then my ratios now become 2 to 4. So I need my dissociated ions to represent that fact. So I need 4 of each. So I'm just going to go 4 rubidiums, ions, and then 4 perchlorate ions. All right, and they're a little bit disheveled, that's on purpose, but they're definitely not a gas, or they would be up and more random. So that is an acceptable particulate showing the correct ratio and state of matter. The last part brings some stoichiometry into it, but it's a bit more complicated. It wants to find mass of the precipitate, all right? So that's how I know it's stoichiometry. It wants us to start with some given amounts of reactant and figure out how much precipitate forms. So the other issue, though, is that these reactants that are described is giving me molarities and volumes. And I know that if I'm going to do anything, if I'm going to do a direct comparison to between the 2 reactants, it'll need to be a mole comparison. And the reason I lean towards mole is since it's giving me amounts of both reactants, that's usually an indication that it's a limiting reactant issue, because only one of the reactants is going to dictate how much of the precipitate is made. All right, so let's do let's figure out our limiting reactant. So again, it's giving me moles and liters, so I'm going to think of this through the lens of the molarity equation. All right, so I've got that in mind, and it's giving me molarity and volume, and I want moles. So to find moles, it's molarity times volume. So let's write this out. All right, now these numbers I'm getting from the FRQ itself. So the first one, let's analyze the, it gives me info on the strontium perchlorate. All right, and it says that it's at 5 molar. Again, I'm multiplying molarity times volume to get moles. So it says that it's 5 molar. Now, it gives me milliliters. I need liters, so I'm just going to convert as I go. All right, slide the decimal to the left 3 times. And I get a mole count of 0.0875. Remember, we're trying to find limiting reactant. Let's find the value for the other reactant, which is the rubidium sulfate. The given values in the FRQ are a molarity of 0.250. And the same volume. And I get a mole count for that reactant of 0.0438. Now, in limiting reactant, the smaller number wins. However, I want to point out that if there was a coefficient up here for one of these, there would be an extra step here. Like if there was 2 rubidium sulfates, we would need to divide the number by 2 to do a direct comparison. If this stoichiometric shortcut confuses you, remember, to find limiting reactant, you can do 2 full grids. You could go straight from here all the way to the product, because remember, it's asking for the mass of the precipitate. So you could do 2 full grids all the way to that mass of the precipitate, and the smaller number would be the final answer. I would rather not do 2 full grids, so I just did this shortcut to figure out the limiting reactant. All right, the smaller number dictates it, and there is no coefficient to mess with it. So what I'm going to do then to finish is convert the rubidium sulfate, the limiting reactant, to grams, because it wants mass of strontium sulfate. So I'll take that number. All right, we got 0.0438 moles. All right. Hey, we're already starting with moles of my given, which is good news. So from there, I can go directly to moles of the unknown. It wants to know about our precipitate. But it doesn't want moles of it, it wants mass of it. Make the diagonals match letters. When moles is over moles, I use coefficients. However, the coefficient comparison between this reactant and this product is still a 1-to-1 ratio, so yay. When grams is compared to moles, it's always 1 mole to periodic table grams, so I need the periodic table of the strontium sulfate. If you add it up, you'll get 183.68. And now we can solve for an answer. All right, we feeling good? Everyone happy? Yeah? All right, well, gonna skip around a little bit. That was Unit 2. I'd like to fast forward to Unit 5. Unit 5 was acids and bases. And I want to look at this bottom question here. This is dealing with the amino acid glycine. That's a acid you studied in bio. And it's going to make a solution by putting X amount of grams and X amount of volume. And when the solution is created, it lets us know the pH. And then we've got just a few little questions on analyzing glycine. Now, here is my formula, or the Lewis structure for glycine, which will be important because it doesn't give me the formula otherwise. So I'll be using this picture, simply counting the atoms in order to create the formula. So let's go piece by piece. Now, A is molarity again, all right? But let's mess with it. So it's one of the most common calculations they'll ask you to do. So our molarity equation, of course, paper keeps moving. All right. Molarity is moles over liters. Now, luckily, one of these numbers is flat out given to us in the problem because it tells us the liters of solution that we're creating. And it says 150 mils. I can't keep that number, but if I convert it to liters, I already have one of my numbers. So to find the molarity, I need moles, but it gives me grams. So I've got a given value of 0.329 in the problem, grams of glycine. Now, keep in mind that I'm going to build the compound from that Lewis structure. And here's what it looks like. And you could put the letters in any order and be fine with the math. So I'm not worried about that. All right, but I need moles, so let's go grams to moles of it and make the diagonal match. When moles is over grams, it's 1 mole to periodic table. If you add glycine up, you will get 75.07. Run the grid, and you'll get an answer of 4.38 E negative 3. And of course, this is the missing mole value. Now, when you're doing the FRQ, you're not going to be drawing all these arrows and stuff. I mean, I'm covering this from a teaching standpoint. That right there is all you really need to show. I'm not covering this well, but just the grid and then the ultimate putting these two numbers into the equation. All right, you can be very straightforward. There's no reason to really overdo your answer. If you're 100% sure of what you are elaborating on, then you can show off your brain a little bit, but you don't want to make the reader get tired of reading your stuff, and you don't want to elaborate so much that you include a false statement, because then you lose all credibility. So just be wise whenever you are really elaborating beyond need. Anyway, I'm just going to do my my plug over here, which will be 4.38 E negative 3 divided by 0.150 is going to give me an answer of 0.0292. And we've got the requested molarity. So let's move into a more acid-base direct question, because now it says find the hydroxide concentration. All right, it's very easy to do. The hydroxide concentration. The problem flat out says that the pH is 2.02. So that's another given value. I know then that pH is not a direct, doesn't have a direct connection to OH concentration like it wants. So I'm going to find the pOH, which of course must be 11.98. How do I know that? Because pH plus pOH equals 14. And how do I go from pOH to hydroxide concentration? Do you remember? We go 10 to the power of the negative value. So 10 to the negative pOH will give me that OH concentration of 1.05 E negative 12. All right, and that's the OH concentration. finally, it wants the equilibrium constant for the acid, for glycine. And it's always funny because this is like the shortest little question, but it requires a heavy amount of work. So here's where your brain should go. We're analyzing a weak acid. How do I know it's weak? Because it is a carbon-containing acid. So it's automatically weak. When we analyze a weak acid in regard to equilibrium, how do we do it? What must we do to the weak acid to get the readings that we need? Here he is. All right. For weak samples, we add it to water in a rice table. So let's start our analysis by taking the glycine and add it to water. This will be Bronsted-Lowry as usual. You should remember that acids are proton donators. So let's give an H plus from the acid to the water. That will result in one less H here and one less positive, right? So it's leaving it negative. And that hydrogen is going to be transferred to the water. Hooray for hydronium. The I stands for initial concentration. Only molarities can go here. And guess what? I know the molarity of glycine because I found it in part A. There's that molarity. So let's get it into this spot. You'll remember that water has no effect on equilibrium studies. And our initial concentration of product is none. C is the change, so let's show our shift. We will always shift toward the zeros. So we want to go down on the reactant and up on the product. Please keep in mind that though it doesn't happen here, that the change row can account for coefficients in the balanced equation. It doesn't really happen in acid-base equilibrium, but it does in general equilibrium, where there could be like a 3 right here to balance the equation, in which case this would say plus 3x. So make sure that you review that. I plus C equals E. So what the heck do we do with this? Well, remember, we are looking for K. All right, it's Ka because it's of an acid. But what does a K expression look like? Well, remember, to find equilibrium, we would always put the concentration of the products over the concentration of the reactants. So if I were to write an unsubstituted equation, all right, I would say that Ka equals, and start with the products, which would be C2H4 O2 N minus is one product, right? The other product's the hydronium. And we'll put that over the relevant reactants, which in this case is just the glycine. So there's that unsubstituted equation that I highly recommended you getting in the habit of drawing. But these values need to come from the equilibrium row, all right? And I don't have any of that. There's variables in all of these, and I haven't solved for x. How the heck do we figure out the numbers? Well, see our friend hydronium there? He has an identity of x. So if I can find the equilibrium value of the hydronium, I can solve for everything. Now, there's a very direct way to solve for the hydronium because I know the pH. So I actually suggest you going that route. However, just for teaching purposes, I'd like to remind you of the other connection that you can do between hydronium, hydroxide, pH, and POH. So see if you remember this. A secondary equation that we used was the fact that the hydronium concentration can be found by dividing Kw by the hydroxide concentration. If you remember, Kw was a constant value of 1e-14. All right, that's on your formula chart. And for this example, we already have a hydroxide concentration, right? We found it right here on part B of 1.05 e-12. So if I went this more indirect route, but I just wanted you to remember Kw exists, but if you divide those numbers, you'll get an H3O concentration of 9.52 e-3. And this is going to equal X, right? Because this X is the hydronium, which is the now found molarity. With that, we can plug and chug now, right? So let's unsubstitute and say Ka equals, and now we just use the equilibrium row, right? Hey, look, both of these are X. So you could put this number twice because this is X. You could go that number times that number. If you remember, my whole job is to save you time. So I would rather write it as 9.52 e-3 squared. Or you can write it multiplying by itself, that times that, X times X, blah, blah, blah. But on the bottom, there is a bit more arithmetic in the equilibrium row because it's a number minus X. All right, and then you just run it. Remember, there are no units for the equilibrium K. All right. At the halfway mark for the day, that gives you any comfort. Y'all have asked 0 questions. My first 2 classes of the day asked many questions, so feel free to speak up. We are now going to skip to Unit 7, Thermochemistry. I like this FRQ because it covers many thermochem areas. It's going to cover a version of Big Mama, and then it connects delta H to delta S to delta G. All right, my enthalpy, entropy, and Gibbs the energy. So let's revisit those together. All right, we've got acid yielding acid at equilibrium. All right, and we've got the Lewis structures for each, along with the bond energies of some different types of bonds. If you remember, the real Big Mama equation states that you'll take the sum of the products minus the sum of the reactants. However, bond energies was the opposite, so don't get it mixed up. For bond energies, it's reactants minus products, the sum thereof. So let's get our work together. Now, all the values I need are here, so I'm just going to go straight across the bonds, and then the bonds have representative values. For example, starting with the reactants, there's an HC bond, and the HC is 413. All right, and then there's a CN bond, and the CN is 891. Followed by a nitrogen-oxygen bond, which is 201. So there's all the reactants. Since it's bond energy, we're doing that first. And your equation needs the difference of these 2 items. All right, so now we'll work into hydrogen to nitrogen, which is given at 391. Followed by nitrogen to carbon, given at 615. And then finally, carbon to oxygen, 745. All right, your calculator will tell you that this equals negative 246 kilojoules per mole. All right, now let's tiptoe away from the math a little bit. And we'll get conceptual, because the next part of the question says a student claims that the entropy, now remember what entropy is, all right? The S looks at disorder. The more disordered something becomes, the more thermodynamically favored it is, and S is positive. But if things are getting more organized, well, that goes against the universe. That is not spontaneous, and that would have a negative S. This says that the student thinks the S is 0, and it wants to know why it's accurate. Now, this is already nicer than it has to be, because a lot of times the FRQ will say, is the student correct, and defend your answer. And this is telling you that they're correct, so you should say thank you to the FRQ gods. But let's talk about how we analyzed S when we were talking. While looking if a reaction is being spontaneous or not, all right? One of the things that we did was we compared the states of matter from one side to another, because we know that the more gas you have, the wilder the movements are. So if we were going from like a liquid to a gas, or even a solid to a liquid, you know, towards the gaseous phase, that increases your entropy. That makes things be less organized, and I would know that S is changing. But look here. it's a gas to a gas. There's no phase change, so it's hard to track any entropy change so far. Another thing that we did, though, is we counted the moles of gas compared to each other, because even if they were both gaseous, if there was, for example, 1 mole yielding 2 moles, well, the side with more gas would again be crazier, would be more chaotic, and would have more entropy. But look at the example. It's a 1-to-1 ratio. So not even the moles of gas are changing. So I would say something along the lines of, this is just a rearrangement of atoms. Now, you would write in more complete sentences and wordier, but just for teaching purposes, all right, shorthanding slightly, but a rearrangement of atoms, right, because there is no change in phase or number of molecules. Entropy is unaltered. So the students write the S is basically 0. And then there's the third part, which really messed y'all up while we were doing this as I graded, because it wants to know which acid is going to be present at a higher concentration. It wants you to defend it based on spontaneity, but it wants to know which of these dudes is winning. Which one's favored? Forward, which is thermodynamically favored, or backward, which would be non-spontaneous. Well, here's what I know. Here's what I would want to be in your brain. I would want your brain to know that thermodynamically favored, bless you, would equal an entropy that is positive and a free energy that is negative. All right? This idea should just be in your brain, and it's a part of the thought process for solving. Now, I want to know, because if it's thermodynamically favored, it's going to be favored forward, and then the product will win. But my problem is that I don't have a delta S, because we just said that delta S is basically 0. So he's not going to help us really. So delta G, though, can help us. Now, I've got enthalpy up here, but I don't have a direct, that's not directly correlated to whether or not it's going to be thermodynamically favored or not. But guess what, y'all? There is an equation that we're not going to use to calculate, but can help us do our analysis, because we get to go all ghetto homies now. Here's what your ghetto homies looks like. Now think through this with me. We decided that delta S has a value of 0. If delta S has a value of 0 and it's multiplying by temperature, any temperature times 0 is 0. Therefore, this equation really becomes delta G equals delta H. All right, because it's delta H minus 0, right? So, okay, well, delta H minus 0, guess what? Is delta H. And guess what delta H is? Boop, 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 doo, doo, doo. Look at that. We figured that out earlier. It's negative 246. So delta G equals negative 246. Therefore, delta G is negative, so it's thermodynamically favored, which means the products are going to win. We're going to end our discussion today close to my hour mark for my voice for y'all with Unit 8 atomic structure. All right, so we're going to look at iron 2 and iron 3. This electron configuration of an ion, y'all messed it up really bad during the unit. So I definitely want to show you this because we have a high probability. So we are, it's iron 2 and iron 3 is what all of these questions are talking about. But we're going to start with the electron configuration of iron 2. All right, so electron configuration, that's going to require a table, right? So make sure that you are still on top of how your configurations work. All right, it goes SPDF. If you number them, S starts with 1, P starts with 2, D starts with 3, and F starts with 4. And that should help with your memorization. All right, we're trying to get down here to iron. So let's start, off ball says we start with hydrogen. All right, so let's go. All right, so let's go with 1s2. There's 2 squares in the 1s. Then we go directly to 2s2, across over to the first p block, which starts as 2p, and there's 6 electrons there. After 2p comes 3s. From 3s over to 3p, whoops, sorry, it's 2 squares in 3s, 6 electrons in 3p. Down to 4s2, and then we hit the D block that iron lives in. So we're going here to iron, and it's 1, 2, 3, 4, 5, 6 elements over, so 3d6. Now, that is not the answer because this is the configuration of, we want the configuration of iron 2, and this is the configuration of iron. How does iron become iron 2? What happens to its electrons? It's got to lose them. What electrons does it lose? Well, we know that we want to get rid of valence electrons because those are the electrons we take, which means even those of y'all that knew you needed to do something with the electrons, a lot of y'all took from there. You made it 3d4. No, no, no. Those aren't valence. Valence electrons, by definition, are electrons in the highest energy. These big numbers are the energy levels, and the highest of them is 4. That's where we need to remove the 2 electrons. Now, hey, there's exactly 2 electrons there, so just get rid of it. And when I say, you shouldn't have drawn it and crossed it out. I mean, you can and rewrite it, I guess, but I'm saying that this right here shouldn't even exist. The answer for iron 2 is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. That's it. Or if you wanted to be extra smart because it didn't tell you which notation you had to use, you could have done this. Noble gas notation. Then you would have to write all that. But notice how even my noble gas notation still leaves out the 4s. Using principles of atomic structure, which iron ion has a larger ionic radius and why? All right, so we are comparing iron 2 and iron 3. Iron 2 and iron 3, and it simply wants to know who's bigger. So right away, it should brutally jump at you that he's bigger. And again, you would be writing these in wordier answers, but the same ideas, all right? Now, how do I know that he's bigger? Well, positive 2 versus positive 3, this guy has to have more electrons. He must have more electrons in order to have a lower charge than him. All right, so he's bigger because there are more electrons in the outer shell. Right? Because less electrons would make you more positive. Well, what does more electrons in the outer shell mean? Well, it's kind of twofold. All right, it means that there's more matter present overall, right? Because electrons are matter. But even bigger deal is that there's going to be more electron repulsion, right? Because one of the things that we talked about that makes that radius, that makes it really start to spread out, is electrons trying to escape each other, all right? And if the electrons are pulling further and further apart from each other, it gives you the capacity for a larger and larger radius. Now, I do want to point out that the other radius thing that doesn't apply here, but that we often talked about, was effective nuclear charge, which looked at the number of protons that were inside the nucleus that were pulling those electrons in, making it smaller. So that's important to know, and you want to have effective nuclear charge handy. But the reason it doesn't apply here is because the items, the species they have you comparing, have an equal nuclear charge. Because even though the irons have different numbers of electrons, they have the exact same number of protons because they're both iron. Iron 3 ions interact more strongly with water molecules than iron 2 ions. Explain why using Coulomb's law. It says, it's admitting to you that iron 3 is better at being attracted to things. And it wants to know why. Why is iron 3 better at being attracted to things? All right, well, it wants to use Coulomb's law, so fine, let's use Coulomb's law, all right, which states that the overall attraction is going to be the charge of species that are trying to be attracted to each other over their radius, all right? So there's Coulomb's law in a nutshell that you should definitely have handy, even though you'll never calculate with it. So why does Coulomb's law support Fe3 beating Fe2 for attraction? Well, I would say that Fe plus 3 has a higher charge, which equals more attraction according to Coulomb. remember these Q's here are the charge. So the higher those numbers are on that numerator side, the higher the answer would be if you had to calculate with it overall, right? And that would make the attraction be higher. But you could even use Coulomb's law from the other angle and say that the smaller radius will allow more attraction, right? Because look at Coulomb's law. There's the radius right there. It's the denominator. So the bigger this number is, the higher that it's being divided by, the smaller the answer is going to be over here, the smaller the attraction is going to be. And how do we know that Fe plus 3 has the smaller radius? Because we spent an entire question a moment ago answering that. Part B had you admit that Fe2 plus had a bigger radius, and it's Fe plus 3's smaller radius that allows for more attraction according to Coulomb. Finally, it asks you a glassware question, which seems out of left field, but it's funny how the wording here can mess you up. It wants you to collect 10 mils of one of the iron samples, and then it gives you 4 choices on what to use. It wants to know who's the worst. Who would be the worst? Now, what's funny about this is that the right answer is almost counterintuitive if you're not careful. And here's what I mean. Oh, I lost myself. I taught you that volumetric flasks are the very best thing to measure with. All right, volumetric flasks are those flasks that just have one graduation. They are only good for measuring a single thing. However, but look at the wording of the question. It says you need 10 mils. You need 10 mils of the iron sample. And who's going to be the worst to do it? The volumetric flask that it gives you the option of using is a 25 mil volumetric flask, which means it's a flask with one mark on it, 25 mils. If you need to collect 10 mils, that is impossible to do in that 25 milliliter volumetric. Now, if you had a 10 mil volumetric, it'd be the best choice. But in this example, it's the worst choice because you can't measure anything in a volumetric flask except for the exact thing it's designed to measure. And this problem has 10 mils, not 25.